everybody, and welcome back to our course on Introduction to Mechanical Micro Machining. In the last class, we have seen some of the sources of errors which will create a problem in the structure, and we have also seen that what are the sources of error and where these errors will occur and what is the outcome or the final product. And now, if you calculate all the things, first you find out the what is the problem in the final product. Suppose it is a surface roughness, then you can find out that what are the errors by which your problem has occurred. Then you can go to the different component of the machine tool where you have found this thing, and then finally find the source of the error. By this way you can actually control the, or you can identify at least the what is the source of the error, and then which way you can control, that depends on the what are the instrument and what are the things you have in the machine tool. So, in that we have started and we found that there are different sources of error in the structure of the machine tool. We started with the structure, and we have seen one video where you can do a thermal compensation in terms of insulating of the different area because of the falling of the chip and putting the temperature sensor. So, it can control or it can calculate the deformation in the structure, so that again it can come back to the original location or the target location, and you can continue machining without any problem. So, let us go further ahead in this case. So, now there are the four different forces over there, and that was creating a problem, and this what we have seen in the thermomechanical errors. So, here we have seen that video, and we found that there are different machines available which can actually respond to a thermomechanical error, and your machine will be still within the acceptable zone or acceptable limit, and you can continue the machining operation. Further ahead, so this is the loads. So, what are the loads? That in some cases the weight and position of a workpiece have a significant influence on the machine geometry. That we have seen long time before also, that suppose you have a table. This is the table where you are putting the workpiece. So, if you put a very heavy workpiece here, what will happen? The table is actually not at the bottom, there is always a base. So, base will deform because of the position of this weight, because many times what happens that we put a workpiece here, and then what we do, we slide the workpiece or the whatever we are putting here, workpiece we are putting a fixture or the vise of the workpiece, then we slide it here. If you do this thing hundreds of times, there is a chance of that there is a wear of this particular component, and sometimes you are sliding, sometimes what we are doing, we are just putting on the top, locating at the top, and then you are just falling it down. So, at that time it will create an impact, and if you are sliding, it will create a scratch. So, after a long time, if you continue in such a way that you are end up with some type of problem in the geometric error. So, this will actually destabilize the whole structural loop, and that will create a problem when you do actual machining operation. And dynamic forces, those are the forces which are in dynamic condition. That means, when you do machining, there are different forces occur, and that will create a problem. So, varying forces such as machining forces. So, machining forces is one of the main source, and then after that the forces caused by the acceleration deceleration, because suddenly our machine, because whenever your workpiece is located here, what will happen, that suppose you want to cut it from the one direction only, correct. So, once your tool is completed this path, what you do, you pull out this tool and then suddenly quickly go to this location, because we want to increase the production rate also. So, here we are not doing machining. So, it will quickly go to this location, rapid travel, and again it will locate to this location, then do the second path. So, this acceleration and deceleration also create a small amount of deformation, because in the geometric error. So, these are the different sources of errors by which your geometry will be problematic. Now, coming to kinematic structure of the machine, how you can define the structure. So, it is defined by the layout of the machine components and their axes, how they are located, and mostly almost all machines are in a serial structure. Serial structures means that one machine axis of motion is actually overlapped, or it is built, or it is mounted on the other one. And now, there are different notations are also available. So, if that is the case, now you consider. So, this is the where. So, this is suppose the x axis, and that does not mean that y axis is somewhere else. So, this is moving in x axis. So, y axis either on the top of this x axis, or it is a below of this x axis. So, this is x axis, this is y axis. So, now here in this case y axis actually it is the below of the x axis, it is on the top. So, now they are overlapping with each other, and because of that there is one person who is Sheward, who has actually provided one notation by which you can get the kinematic structure from tool to the workpiece. Now, you have to do that. Let us see that which way we can define those things. Now, this is one of the structures. So, now here some of the notations are given. So, T is belongs to tool and W is the workpiece, correct. Whatever is in between these two, these are the different motions which are coupled with each other. So, now if you see this T, so T is located here. Now, what comes next to T? T is the C axis, that is the rotation of the tool. Rotation of the tool. Now, where this spindle axis is located? This is located on the Z axis. So, now third one is the Z1. Now, where Z is mounted, all the things are mounted is this location. So, from here to here it is there, from here it is moving to the Y. So, now next turn is the Y. Where Y mounted? So, Y is located here. So, this is the Y motion. Y is connected with the x1. So, now from Y to x, so we are getting Y to x, and x is mounted onto the base. So, it is directly connected with the base. So, now this one is the base, and from base we are putting the workpiece. So, this is called the cantilever type configuration, and where we can notate give a notation something like this. Now, this is the second structure. Now, this is a gantry type of structure. So, here again let us see same way. So, these two things are always fixed. Mostly you will get, and you can get Z also, because tool is rotating and rotation is always in the Z axis. So, these three are mostly common in all the cases. W is always at the end, because this is the only location where you are coupling the all the things. So, because we know that this is the workpiece and this is the tool. This is the tool and this is the workpiece, and this both the things are only the open link out of this full loop. Rest of the things are connected with each other. So, after Z, now you can see this is the Z and Z is connected with the Y. So, Y turn is there. Now, it is a gantry type of thing. So, it has a two platforms. So, here is the one, other is the Z, this one. So, that is why it is given x1 and x2, but both things move, we assume that both things are moving parallel and there is no any type of lag in the motion. Then both the things are located in the B and then B to the workpiece. So, this is classification of under case. This is the column type. So, here also, so tool, workpiece, tool, RPM and the Z axis are common for that, and then Z is connected with the Y, then Y is connected. Now, here it is different. Now, if you see here Y to X, everywhere Y to X, and then it is on the B. Now, if you see here Y, it is going to the B, because Y is connected with the base and X axis is mounted on the base. So, now there is a shifting or interchange of the X and B position, and from X you are putting a workpiece on the top. So, that is another way, and this is under 5 axis machine. So, now you have to add one extra axis here. So, here again the same thing here, T, C and Z available, T, C and Z available. So, here is one C and Z is on the Y. So, it is coming to the Y, then Y is mounted on the X. So, that is the X, this is the X1, whatever we are showing here, this is the X, then X is on the base, it is on the base. From base we are putting a B axis is the rotation around the Y axis. So, this is the Y axis rotation, this is the Y axis rotation. So, Y axis is here. So, we have rotation around the Y axis, that is why B is coming into picture. Then we have rotation of the workpiece along the Z axis. So, that is why under C has come here. So, this C is always appear here, because it is a rotation of the tool, and this C is, and that is the rotation of the tool along the Z direction. This is the rotation of the workpiece along the Z direction. So, this one has a under name. So, this is only C which is at this location. So, now by looking at this particular notation, we can see that which way our tool or the kinematic structure is configured. So, depending on that you can find out the what is the structural loop and what are the problems associated with the different axes. Description of the geometric error. So, error of a machine tool are relative motion error between the tool and the workpiece. Now, each movement of a machine tool axis can be described by a 6 degree of freedom, 3 translation, 3 rotation. So, that we have seen here. So, these are the 3 axes x, y, z, all are perpendicular to each other. So, if there is a linear motion, that we consider x, y and z are the linear motion, and the rotation around the x, y, z we can consider those things as a rotation around x is a axis, rotation around b is a rotation around y axis is the b axis, and rotation around the z axis is the c axis. So, these are the nomenclature, we have seen this thing long time before. Now, coming to the flatness, straightness and the smoothness of the motion, because all these 3 are important. Flatness will ensure that you are getting a flat surface on the component. Straightness will ensure that you are not getting any type of if it is a component is flat, but you are getting error from the side, then it is a problem. And the smoothness means, that means there is no any type of fluctuation of the motion, you are getting a uniform motion. It is not like a jerk type of motion or something called the stick slip phenomena. So, kinematic entities of machine are assumed to be perfect, but mostly it is not the case. What we assume, the spindle, if you consider spindle, we assume that single axis of rotation, there is no any other deviation which coincide with the geometric axis of the rotating joint. So, now what is that means, that suppose we have a spindle. So, spindle has one axis, then we have collet, and in the collet we are putting a tool, correct. So, these are the small sub assemblies, and we assume that whatever is the, let me give different color to the tool. So, this is the tool, and tool has is also one axis, correct. So, we assume that rotation of the, this is the single axis rotation. So, this axis and this axis are coincide. So, axis of tool and spindle are coincide, right. That we assume, but many times what happens, it is not the case. You have to be very careful in selection of the tool holder. And if you consider slide, what we assume that they travels in a straight line with only 1 degree of freedom. So, if you consider that your table, suppose this is your table and you are moving in the x direction, we assume that it is not moving in this direction, not moving in this direction, or not actually creating any problem in this particular direction. So, that is we assume that there is no tilting or swaying in the motion. So, this is our assumption, but when you make a construction of the component, all degrees are, all axes are orthogonal to each other, there may be some problems by which you are not able to get the required motion. So, you have to be very careful in getting some machine component out of this type of problematic errors. So, but this is not the correct thing, because we assume all the things are perfect, but this is not correct. So, now let us take this example, that which way we can tell that. So, now consider, so this is one component. Now, what is this component? So, here it is a round object sliding within a bore, right. So, this is the round object, whatever is this is the round object, and this one is the bore. So, whatever is this one is a bore, correct. Now, we consider that when you are rotating this particular thing, this is, if you are rotating the bore, then what happens, that you can actually rotate without translation, right. So, what are the ways you can get this motion? Rotation without translation, right? It is possible, and if you want translation without, that is also possible. Now, if you are moving just this way, means translation direction, then it is possible. That means you are just moving to and fro direction without rotation, that is possible. If you do not want to move in to and fro direction, you fix at one location, you rotate the particular this middle part, that is called the round object, then it is also possible. So, both the things are independent. So, these things are independent. Correct, and that is why it has a 2 degree of freedom. So, this is called degree of freedom. Now, let us continue further. Now, consider we have same thing now here, but instead of this what we are doing, that we are putting a thread here. Okay. So, now only difference is that we have thread on the both the side. Consider this one is a bolt and this one is a nut. So, now if you are rotating it, translation will occurs automatically, because now both things are coupled. Only what we have done, that we have just put thread only, nothing else. So, now we can tell this is only single degree of freedom, because you cannot get independent motion. If you want to rotate without translation, it is not possible, because when you rotate automatically it will translate inside it, and if it is just a translation is not possible, because you have to rotate to get the translation motion. So, those both the things are coupled with each other, and that is why it is called the 1 degree of freedom. So, how this thing is connected with the machine tool? Because in this machine tools, motions are assumed to be 1 degree of freedom only, because we understand that when you are moving a cutting tool in x direction, we assume that it is moving in x direction only, and if you are moving in y direction, z direction, whatever way, you assume that this is a single degree of freedom, but that is not the case. Every time your motions are coupled. If you have problem or if you have error in one axis, it will be actually reflected in the other axis also, and that is why it is more problematic in a machine tool. It is not the true, because motions are coupled, and this further leads to the machining error. So, now let us see some examples that how these things are coupled and which way it will create a problem in the machine tool. Right. So, this is the flatness and straightness error in the linear state. Now, if you consider this particular diagram, your whole table is moving in the x direction. So, this is the direction of the x motion. So, now there are two errors, one is the straightness error and another one is the flatness error. So, how you define the straightness error and flatness error? So, runout of a linear stage is the linear portion of the off axis error. So, off axis means that we intended to move in the x direction, but it is moving in x direction along with the some deviation in the y direction in the z direction. So, first one is the flatness. So, let us see this, what is the flatness. So, it is a displacement error along the z axis. Now, see, consider this is the table. Now, table you want to move in this direction, but your table is suppose moving in this direction. Suppose there is a little bit of problem. So, this is the direct problem. So, whatever is this problem in the x direction, that means it is moving up and down, and then it is moving in this direction. So, that particular displacement error is called the flatness. So, your surface is not flat completely. So, you want to do a cutting, suppose this is the workpiece, you want to cut a flat surface here, this is the surface which you want to cut. Now, consider your z axis, that means your tool is located here and your x axis is traveling in this direction. So, because of this flatness error, what you are getting instead of that, this is your workpiece again same, what you are getting is some type of this type of things, that is because of the flatness error. Let it be at a micro level, but that is still enough to get rejected during the inspection. So, that is called flatness error. Second with the straightness error. What is the straightness error? The same displacement error, but not in the z direction, but is in the y direction, in this direction. So, here what it is doing, Here your table is not moving along the x direction, but it is actually moving in the y direction. So, where it is creating a problem? Now, if you consider that suppose your workpiece is this one, correct. This is your y axis, this is your x axis and this is your z axis. You want to flatten out this particular surface, okay, this surface, because you have a reference position or some other different type of features which you have found or which you have calculated based on the reference of this particular surface. So, you are cutting this particular surface to make it completely flat. So, if you see from the top, now this is our workpiece and our tool is located at this location, right. So, what is our object? That we want to remove this material up to this much amount of material we want to remove, and it should be straight line. But what happens, what we are getting here, that because of this problem you are getting a some type of unevenness, because that is because of the problem in the y axis. So, this is still our y axis, this is x axis, and from through the page our z axis is located. So, our tool is located here. So, these are the two problems because of the problem in the flatness and straightness run out of the linear stage. Now, let us take this example. So, now this particular thing, this is our ideal flat surface, whatever is this straight line is there, this is the ideal flat surface. And what is our error surface? So, this one is a error. So, now this is the problem, the surface is not flat, but instead of this flat you are end up with a one type of other surface, and so this is your surface. Now, we can understand this thing that our error is in x direction only. Now, suppose you consider this is the x direction and this is the z direction, correct. So, we have error in x direction and this is our original location of the component. Our component or the workpiece should be located here. So, this is the location of the workpiece. If the surface is flat, but surface is not flat here, we know, then our workpiece is here. Now, its location is this one. This is location of our workpiece. So, if in first case that this is the actual location of the tool, suppose you have a tool position, this is the actual location of the tool, but because of this flatness in x direction, what we are getting? We are getting a shifting of this particular axis and this is our actual position. This is the desired location, but because of this flatness error in the x direction, you are getting this problem. Now, what is the problem here? That even though there is a problem, there is a deviation in the x direction. So, what we are getting here? That we are getting a shifting in this particular direction. So, this is in x direction. So, let us our error or the deviation in dimension should be also in x direction, but if you see that this dimension change is also there and this dimension is also there. So, you have vertical error also, because this is displaced at this location because of this angle theta, and because of that you are end up with a two dimensional error, because one is in vertical dimension, another one is in horizontal direction. So, now what is the conclusion of this thing? We have seen in earlier slide that motions are coupled with each other. Even though you are getting an error in the flat direction or in any one direction, actually you are getting error in two different directions. So, it is better that you first identify which is the error and then you actually do a program, because if you do not consider this flatness variation here, you are end up with not only wrong dimension at one location, you are end up with the wrong dimension at two locations. So, this is what it explains about the flatness error at the tool and workpiece location. Now, row pitch and yaw angular run out of the linear stage. Earlier we have seen that there was a flatness and the straightness error, but now consider suppose there is a rotation also. So, now that angular run out is the angle measured between the actual motion and the ideal straight line motion of a linear stage. Now, this is our linear stage, this is the travel, and we were rotating in this direction only. So, that is the rotation around the x axis. So, if that is the case, then what will happen, that our z axis will create another rotation here. Suppose it is not exactly at the flat direction, then it will create a pitch, that is the rotation on the y axis. Yaw is called rotation around the z axis, and the roll is called rotation around the x axis. So, it has a 3 orthogonal components, one is the pitch, another is the roll, and another one is the yaw. So, not only the translation motion, but you are also end up in the getting a error in the 3 rotational axis, that is by of the pitch, roll, and the yaw motion. Coming to the smoothness of the motion, now we have seen the straightness, flatness, but smoothness is also very important in the micro machining, because smoothness is related to the stick slip behavior of stage, bearing, or the drive mechanism. Because if you have seen a manual machine, if you have operated the turning machine, and if you are doing a operation, now consider, so this is your workpiece, this is the chuck, and this is your cutting tool, and you are moving in this direction. So, when you are moving in this manually, this is, let us consider manual lathe machine. When you are doing in this direction, at that time what happens, it is very difficult to get a uniform motion, right. When you rotate a carriage wheel, at that time it is very difficult to give a continuous motion, and because of this is because of the steep slip behavior, because there is a friction between the different components, and you have to overcome that friction uniformly, and that is very difficult when you operate at a manual operation, right. So, this is what is happening, this is the frictional force. So, frictional force will increase initially. So, you are actually not able to get a continuous motion. So, this is stick flash, and as soon as you actually overcome that frictional force, suddenly you are able to move it, and then this is called slip force. And once that motion is over, again the same cycle will repeat, again you will get a stick phase and the slip phase. So, your motion is actually not uniform. What we need here in this case, that we need a continuously this type of friction, that friction force should be uniform, so that you can get a uniform motion out of this particular motion, but that is not the case. So, what happens because of the lack of smoothness, the sudden jump in the motion followed by a period of no motion, correct. So, now if you see this particular thing, this is the time. So, within this particular time you have very difficult to move in this direction, but after that you are not getting a friction enough, and suddenly you are moving that part, again it is coming to a standstill position. So, you are not getting a uniform motion, and because of that non-uniform motion, what happens, that you are getting a very high relative forces for a brief period, because whenever you are getting a sudden jump, in this case at that time your forces are very high force, and when you are getting a no motion, at that time there is no any type of failure, because at that time there is no any type of forces in that, or forces are very less. So, if this type of high fluctuation of the forces are there, then what it will directly lead? It will lead to the failure of the cutting tool, right. So, because our objective is to make sure that there is a uniform and the very less amount of forces acting on the workpiece and the tool during operation, but because of the steep slip phenomena, you are not getting uniform motion. And sudden jump can also be a source of the vibration if the stage is very heavy, or is supporting a massive workpiece or the other structure, because we know that friction has direct connection with the normal force, because if your things which are very heavy onto the stage, so at that time you have to provide more amount of force initially, and as soon as you are crossing that particular frictional force, you are getting a jerk motion, and again you are end up with the low motion. So, because of this smoothness or stick slip phenomena, what is happening, that you are not able to get a smooth motion, and that is resulting in the abnormal machining operation and the failure of the cutting tool. Let me finish this lecture here, and we will continue this topic further in the next class. Thank you very much.